Derived data types are quite useful because they allow to transfer any combination of type data. We also will have to deal with some more advanced features about alignment and resizing for correctness and performance. MPI data types. So in the previous chapter, a message was always a contiguous sequence of elements of a basic type. So it would be the address, the buffer, the count, and the data type handle. And the data type handle would be an MPI character, an MPI integer, an MPI double, or whatever. Now, the goal in this course chapter is to transfer any data in memory in one message. So that could be strided data, portions of data with holes between them. That might be, for instance, to send columns of a two-dimensional matrix in C, or a row of a two-dimensional matrix in Fortran. So it's also possible to combine various basic data types within one message. So obviously you don't want to send data in multiple messages if you can avoid that, because it would incur multiple latencies, and that's not what you want. You also don't want to copy data into contiguous scratch arrays, because that would waste memory bandwidth and hence CPU time. So the method is to create data type handles. The memory layout of send and receive buffers can be defined that way. For basic types, we already discussed that. For derived types, there are very many of them. So for instance, vectors, subarrays, structures, and some others which you will encounter. So message passing goal and reality may differ, and also this has to do with parallel file I/O. Derived data types are a very important part of expressing input-output patterns. So consider a C struct, and that has 3 integer values and 5 double precision values. So struct buff layout is the type in C, buffer is the variable. And if you look at that, what the compiler does with it, it will actually have 3 integers, and then a whole, and then 5 double precision numbers. So that is typically what would happen. Now, in MPI send, we would like to send buffer as one entity, as one buffer data type. And the way to accomplish this is to have an array of types, an array of block lengths, and an array of displacements. So there would be, all these arrays would have length 2, and for the first 3 elements of the struct, those are of type MPI int. And the block length obviously is 3, because there are 3 of those. The value for the displacement of that particular part of the struct is of course 0, because it starts at the beginning of that particular struct. And then the second block is in fact consisting of doubles. So the type would be MPI double. The block length would be 5, and the displacement we will discuss later on. So then we can create a new data type using MPI type create struct. We indicate the number of types and of block lengths and so on by 2, and then we have the array of block lengths, the array of displacement, and the array of types, and the address of a buffer data type. Once we've created the type, we have to commit it. This can be done with MPI type commit of the address of the buffer data type. So a derived data type is logically a pointer to a list of entries. Basic data type at displacement. So basic data type 0, displacement of data type 0. Basic data type 1, displacement of data type 1, and so on and so on. And of course, the matching data types. So lists of basic data types must be identical, and the displacement, of course, are irrelevant in the programming language because basically that's the compiler's job. Now let's take an example at a derived data type handle. So this is a more complicated example where we first have an MPI character. It's the first thing which we want to send, so basically the displacement will be 0. And then we have an integer. The displacement of that will be 4, because basically an integer typically is 4 bytes, while a character is 1 byte. And the compiler will actually place that integer at a 4-byte boundary, which means that there are in fact 3 bytes between the character and the integer which form a gap. The second integer would be at displacement 8, because an integer is size 4. And then we have an MPI double, and here again there is a gap of 4 bytes, because typically a compiler will try to align double precision numbers at 8-byte boundaries. So basically not at 12, because that's not divisible by 8, but at 16. So a derived data type describes the memory layout of structures of common blocks, subarrays, some variables in memory. So that's essentially the idea. The simplest derived data type is in fact contiguous data, and that just consists of a number of contiguous items of the same data type. So we've got old type, and a repetition of that forms a new type. So MPI type contiguous takes the count of the old type, the MPI data type old type, and the new type. Of course, the address of that, and similar in Fortran. So this is very convenient, for instance, in order to transfer rows or columns of matrices in C and Fortran respectively. A vector data type is also quite useful, and we have the old type, which could be, for instance, MPI double or MPI integer, and then the new type. The new type consists of blocks and strides between them. So basically here we have blocks with a block length of 3, that pattern repeats, and a stride of 5. So that means that there are holes, because basically the stride dictates that the next block starts 5 units of old type further on. And holes that should actually not be transferred. So basically the new type will not have holes at the end. The count in this case is 2 blocks. So we have 2 blocks, block length 3 each, stride 5. We do that with the call to MPI type vector, which takes the counts, so that would be 2 in this case, the block length, which would be 3, the stride, which would be 5, the old type, and then the address of the new type. Struct data type allows you to combine basic data types or other data types which are not all the same. So we have old type, for instance in this case we have 2 of them, MPI int and MPI double. And we've got a block of 3 integers followed by a block of 5 double precision numbers. So we've got 2 blocks. And now we need to specify the length of the blocks, the displacements of each block, and the type, the old type of those blocks. So that works with MPI type create struct. We specify the count, an array of block lengths, so in this case 3 and 5, an array of displacements, so that would be 0, and then the address at which address 1 as indicated in the figure, and MPI data type, so MPI int, MPI double in this case, and then the address of the new type. So here's the example. The count is 1, and the displacement would be address 1 minus address 0 for the second block. So the memory layout is fixed in C. So basically we have a struct int with an array of 3 and double with an array of 5. For Fortran, that would be similar for common blocks if you're still using those. So also an integer array of length 3, double precision array of length 5. Of course, you would be more likely in modern Fortran to have derived types, and in that case it's quite important that the new type is defined as sequence, because that tells the compiler that it should not change the order of the different fields in your derived type. Otherwise, if you don't specify sequence, the compiler can do whatever it wants, and you will have a hard time to actually get the displacements and the arrays of types correct. There is an alternative, but basically that is slightly frowned upon, so that's not portable, so let's just not consider it at all. How do we compute the displacements? So the array of displacements for block I is in fact the address of block I minus the address of block 0. And in C++ you could just try to get away with pointer arithmetic and the address of operator, and that would kind of work, but it would not be really portable. So a better way is to use MPI get address with the address of the buffer, and then an address of an address variable of type MPI a int. In Fortran you do the exact same thing. So how to compute the actual displacements? Well, there is a function for that, which is MPI a int diff. It takes the first address and the second address and returns the difference in addresses. So address 1 and address 2 are absolute addresses. The difference is just a number of bytes. And the same works in Fortran. So note that the kind of an address is MPI address kind in Fortran. It's also possible to compute a new absolute address from an existing absolute address and a relative displacement, so basically a number of bytes if you wish. And that can be done with the function MPI a int add. And that takes an absolute address and the displacement. Both are of type MPI a int. And the same applies to Fortran. So here's an example for the structure we have already been considering. So basically for we get the address of the send buffer, the integer array element 0, and the address of and we put that into the variable I address 0. Then we get the address of the send buffer, but now for the double precision array, first element, D0, and we put that into I address 1, and then we can compute the displacement, which is the difference between I address 1 and I address 0. So for Fortran it would be quite similar. We have the type buffer type, its sequence, integer and double precision, integer 3, double precision 5 values. And again we use MPI get address on the buffer element field I, first element of that array, put that into I address 0, and similarly for the D field, again first element, so sound D1, and put that in address I address 1, and we compute the difference. So that's an easy way of computing the displacements in order to create a struct type. So before a data type handle can actually be used in message passing communication, it has to be committed. and that's done with MPI type commit. And that needs to be done only once by each MPI process. So if you do it multiple times, it doesn't really matter, it's just no ops. So the function signature is MPI type commit, is the name, and then just the address of the new data type. And if you don't need it anymore, you should use MPI type free in order to free up a data type and the internal resources it consumes. Failing to do so may lead to memory leaks, so it's good habit, good practice to actually pair an MPI type commit with an MPI type free. So of course, what's the fastest? With strided data, you can use derived data type handles. You can copy strided data into contiguous scratch send buffer communication and so on. Or you can even do communication routines. What should you do? Actually, the answer is not in the MPI standard, because basically the idea is that your programs are portable, but not necessarily the efficiency. So basically it depends on the specific hardware you're using. So when talking about data types, there are a few notions which we have to keep track of. So on the one hand, there is the size, and that's the number of bytes that has to be transferred. There's also the extent, which spans from the first to the last byte, and that will include all holes. So also holes at the beginning or the end of a data type. The true extent spans from the first to the last true byte, so that would exclude the holes at the beginning and the end of the type. Automatic holes can be added at the end for alignment purposes, and that is sometimes a requirement of the compiler. Additional holes at the beginning and the end can be set by lower bound and upper bound markers with MPI create resized. Basic data types, the size is the extent, is the number of bytes used by the compiler. So that's the simple rule for basic types. And you see that illustrated here. So the old type would be given like this, and there would be an alignment hole at the end. And then we have 7 of those, if memory serves. 1, 2, 3, 4, 5, 6, 7. And we get, for new type, we get an LB marker and a hole at the beginning. We also have the UB marker and 2 holes at the end. So basically the true extent is in fact 7 times the extent of the old type. The size is actually 5 times the old size, the old type, because we have 5 actual values. Those are holes, they do not count towards the size of the data type. So we have the LB address and we have the true LB address, and we have the UB marker and the true UB marker at the end. So the true extent is 7 times the old extent. So Fortran derived data types and MPI create struct. So we need to either use sequence and or bind C for derived application type, so that it can be used as buffers in MPI operations. So the bind C is pretty useful as well. This was added in MPI 3 actually. So alignment computation of basic data types, it is in fact undefined by the standard, and there is nothing in the standard that defines it. So it may depend on compilation options. In MPI 3 and 3.1 it's still undefined, but it's recommended to use a bind C environment, so basically an additional type specifier. The compiler may add additional alignment holes, and it will do that within a structure. So for instance, between a float and a double, or an int and a double. It may also add them at the end of the structure, so after elements that differ in sizes. And there are examples of that in the MPI specification. Alignment holes at the end is of course important when you're using arrays of structures, because then you create a lot of holes between each consecutive array element basically, and that is quite important. So the implication of that is that if an array of structures or derived types in Fortran should be communicated, it's recommended that the user create a portable data type handle and applies additional MPI type create resize to this data type handle. And there is an example in the specification. We'll also see an example later on. Holes due to alignment gaps may cause loss of bandwidth, which is obvious because basically you're sending no information while it nevertheless takes up space. So by definition, MPI is not allowed to transfer the holes. So basically you should fill the holes with some dummy elements, and again there is a specific an example in the specification. So there is a correctness problem with arrays of structures. So there is the possibility that the MPI extent of a structure is not the real size of that structure. That is because MPI will add alignment holes at the end, because the MPI library has wrong expectations about what the compiler is going to do. So for basic data types within the structure, or for the allowed size of the whole structure. So for instance, multiples of 16 bytes. So the solution in C is to call MPI type create resized with LB, so the lower bound equal to 0, and new extent is the size of one structure. Or you can use the same thing in C and in Fortran. You can compute the addresses, the get the address of the first part of the structure, the address of the second part of the structure, then compute the extent as the difference between the second address and the first address, of course using the MPI routine for that, and then call MPI type create resized with the old structure type, the lower bound, the new extent, which is just the difference of the addresses, the correct structure type, so the new one, and that would give you correctness. So the correctness problem, here is an example with C. So basically we have double and int structure. So essentially if you compile that, you would see that MPI type extent is not the same as size of and real size. So basically for portability and correctness, with arrays of structures, the data types should always be resized. Here's another example. In this case, this is on a cray, and in some circumstances it actually does it correctly. But basically that is unfortunately non-portable, so you would have to resize anyway. So there are also performance issues with holes in structures. The correct solution for homogeneous and heterogeneous solutions is to add dummy elements to fill the holes in the structure and in the data type. In a homogeneous environment, you could use MPI byte as the type to transfer, and then transfer the whole structure as an array of bytes. But be very careful, because you might get into trouble on heterogeneous environments. So large counts with MPI count. So MPI uses different integer types. So int and integer, MPI aint, that is actually an integer MPI kind address kind. So basically that is an integer that is large enough to store addresses. And there is also MPI offset, basically for absolute addresses as well, and that again is large enough to accommodate. And then there is MPI count, which again is large enough for your larger counts. So what you know is that size of int is less than or equal the addresses kinds, so basically MPI a int and MPI offset, and that MPI count is potentially even larger. So all count arguments are int or integer. Real message sizes may be larger than due to the data type size. So MPI type get extent, MPI get true extent, MPI get size, type size, MPI type get elements will return undefined if the value is too large. So basically, if you work with really large amount of data, but yeah, that should be really huge, then actually you're guaranteed, if the size is too large, that you'll get something detectable. Okay, this we skip. Then some other derived data types. So there's also the subarray data type, and this you can create with MPI type create subarray. That would extract a subarray of an n-dimensional array, and all the rest are wholes. So basically that's ideal for halo exchange with n-dimensional Cartesian data sets. So for instance, for a 3-dimensional data set, a halo would actually be 2-dimensional. So depending on which edge of your 3-dimensional data structure you're transferring, that would of course be a subarray, like a slice out of that 3-dimensional data structure. So it's quite similar to MPI type vector, and it works primarily which would work primarily for 2-dimensional arrays. So you could view subarrays as the multi-dimensional extension of that. And we'll see an example in the next chapter. There is also MPI create darray, which is again a generalization of the subarray, and we will see an example later on. So basically there have been a few things in the MPI1 interface which have been substituted by other things in MPI2 and MPI3, and basically you're strongly advised not to use the old ones, obviously. It's also possible to pack and to unpack several data items into one message buffer and communicate buffer with data types MPI packed. So that is possible, however typically it is not so very useful except in cross-messaging between different MPI libraries. Whether you really want to go that way is, let's say, it would be very hard to do that correctly, so it's probably not the best idea. Other MPI features, so MPI bottom we already discussed, that was to compute absolute addresses, and especially in Fortran where you don't really have pointers. This is actually the same slide which was already discussed in the chapter on virtual topologies. So again, performance. What is better? Well, again, nobody really can tell you, except that, well, let's say the standard really can't tell you, and you would have to experiment a little bit in order to see what works best on your hardware platform.